Afternoon, everyone. My name is Skyly McLean and I work for the Limestone Coast Landscape Board as a Regional Agriculture Land Care Facilitator. On the behalf of the Limestone Coast Landscape Board, I would like to thank you and welcome you to our second webinar on the Healthy Soils series. To begin with, I would like to acknowledge and respect the traditional owners of the ancestral lands of Potterwich to the north, Jarwajali to the east, Bowendick to the south, and Miantung to the west of the Limestone Coast region. We acknowledge elders past and present, and we respect the deep feelings of attachment and relationship of Aboriginal peoples to country. So our presenter today is Mel Fraser, and I am hoping that she is feeling a lot better. And thank you for everybody for understanding and rescheduling till today. So a little bit about Mel. She finished her schooling in Adelaide and she moved to the Eyre Peninsula to take a gap year on a family farm. It was while she was there, she was rolling around the paddocks with an agronomist collecting soil samples, and she became hooked on agricultural science and her passion for soils began. She has studied at Roseworthy campus, which was a Bachelor of Agriculture, and then also went to Guelph in Ontario, Canada. She's worked in farms in Queensland and then was called back to Adelaide to commence her PhD in soil science, which explored the soils at Avenue Range near Callira and the impact on the Fairview drain. After finishing her PhD, she then went to the NT for 4 years and decided probably that was too warm, and she moved back to Narracourt, where she now works at Rural Solutions. She really enjoys working across research and extension with an emphasis on sandy soils, calcareous clays, and cover cropping and regenerative agriculture. Her local knowledge and experience puts her in high demand, and I feel very lucky that we have Mel here today to take us on the journey to learn about fertile soils. So I will hand it over to you now, Mel.
Thank you so much for that introduction, Skyly. And again, thank you everyone for joining me today. Apologies, I wasn't able to make it last week. I came down with a terrible cold and spent the week in bed. So I've done my best to pull together today's presentation, but forgive me, I'm still a bit foggy in the head. So I'm going to give it my best shot. But look, if it all goes pear-shaped, Skyly will just record it again, okay? And then make that one public. So for those of you joining me today, thank you. And hopefully you find this next 40 minutes or so informative and enjoyable, and you come back at me with lots of questions. So like Skyly said, the second in our series of webinars is really to look at what makes the soil fertile. And I guess, you know, we came up with these titles a little while back when we were doing the contract for these webinars, and I didn't give it a whole lot of thought at the time, and I'm sort of come around to try and write this webinar and put together the content for it, and thought, oh, what makes the soil fertile? Maybe it should have been a different title, because really what makes the soil fertile is more than just fertilizer. So perhaps we could have named it, you know, Understanding Soil Health or something like that. But here we are. And so what I'm going to talk to you today is really about soil fertility, and the fact that soil fertility is determined by the combination of our physical and chemical and biological properties and processes in soils. And some of these are inherent. So this is the stuff that you can't change. You know, the parent material that our soils were derived from, the way that they were blown in or water brought in by water into our landscape. And you can have very little impact over those, and others that are more dynamic. And so these are properties and characteristics of soil that we can actually change and alter via our management practices. So that's what I'm going to talk to you today about. I thought we might just start by actually reviewing recently the Department of Environment and Water and the Landscape Boards and PIRSA came together to try and define what we thought, you know, is a healthy soil. You know, what is the definition of a healthy soil? And the definition that they came up with was, You know, a healthy soil really maintains the landscape function and environmental quality, and it does this by both you know, regulating water and oxygen and gas exchange cycles. It provides biodiversity and shelter and habitat for a range of different animals and plants. It helps to regulate our climate, and it does this, of course, by cycling carbon through soils and managing the emissions of carbon dioxide and oxygen and you know, methane and nitrous oxide, you know, back through plants and soils. And it sustains biological activity both above and below ground. And what do we mean by this? It means soil gives life, and not just life to the plants that grow above it, but also to all of the organisms and the plants that explore and grow beneath the soil surface as well. So a healthy soil really does have both of those communities. It's not just plants and things that we can see above ground, but it has a living biota below ground as well. It's fit for purpose. And, you know, what do we mean by fit for purpose? And as I guess you know, I'm guessing that most of the people here are either farmers themselves in some form, either in horticulture or agriculture or viticulture or forestry, or consultants in that space. And so the purpose of our soils is really that end use. What is it that you're using your soils for? Is it for growing grapes or for growing, you know, pastures? Are you trying to remove grain, or do you want, you know, milk? That's the purpose of your soil. That's what you're trying to produce from it. And really the function of that soil and the properties of that soil have to be fit for that purpose. So, you know, your soil really has to have the fitness and all of the characteristics and health behind it to be able to produce what you're trying to produce from it. Because of course, a healthy soil promotes our plant, our animal and our human health. So it's not just a medium or a substrate that holds up roots. This isn't a hydroponic system. There is a relationship between the soil and the microbes in the soil and the nutrients in the soil and its parent material and the plants that are growing in it. And we need that to be functioning so that we can grow good plants with good nutrition, which then produces good animals with good nutrition, so that we can then grow good humans with good nutrition. And of course, a healthy soil then that underpins all these things is, you know, it's productive, so we can remove some product from it. It's resilient, so it can bounce back from, you know, adverse events such as drought or flood or fire. And it's also profitable because, you know, in the agricultural context, like I said, we're in this game of producing resources from the soil. And so we need to make sure that we can keep it healthy so that it continues to do that for us into the future. So soil health really is the ability of the soil to function as a living ecosystem in relation to its natural capacity. So, like I said, in the agricultural context, which I'm guessing is where most of you are interested in either of the industries through here, like I said, forestry, dairying, you know, red meat, wool, cropping, whatever it is. Really, it's these last three components of soil health that that we should be interested in. You know, is our soil fit for purpose? So for the purpose that we're using it for, and are we managing in a way that can promote, you know, good health outcomes? And is it productive and resilient and profitable? At our last webinar, Claire and I introduced the geology and the evolution of the landscape through the Limestone Coast, and we had a look at the major soil types. So, you know, of the 13 soil groups, we've got 52 subgroups or something through the Limestone Coast. So lots of different soils. The predominant ones are our sandy soils, which are generally up on our dune complexes, and then of course we have our heavier clays down on our flats. And you can see just in the photographs that are here, obviously we've got a red terra rossa and, you know, the red loam soil, which is obviously supporting some wine grapes there at Coonawarra. So in that case, that soil needs to be fit for the purpose of producing grapes. The photo in the middle at the top is actually a potato crop, which is growing also down at Coonawarra, but on the black soils of the plains down there. So that particular clay soil obviously needs to be able to meet the demands of that potato crop. Which is going to remove, you know, up to sort of 60 tonnes of produce per hectare. And the photo below is actually from the northern part of our region, and it's a wheat crop growing on a very sandy soil. So you can see that the characteristics of the soil really determine the types of crops that we can grow on them. But sometimes we might be pushing the boundaries, and so we need to know, you know, even if you have been growing a certain crop on the right soil type for a long time, is it still functioning to its full potential? So really, if we're thinking about soil fertility, it's really determined by 3 key properties in the soil and how well they're actually functioning. So obviously we have these physical properties in the soil, we have chemical properties in the soil, and we also have biological properties and functioning in the soil. And these 3 systems are interdependent. They do influence each other, which then influences on what will grow above the ground, and then how nutritious that is and how healthy those systems are at the end. So what I'm going to do today is just run through, I guess, some of the key indicators of fertility, of physical and chemical and biological fertility, really as an introduction to these soil properties. And then when we join you again, actually at the next webinar, my colleague Amanda Chappell is going to be running you through organic carbon and biological function in soil. She's going to do a bit of a deep dive into those in the Limestone Coast. And then when you join me after school holidays in August, July and August, I'll be talking about these particular indicators and how to detect them, what to look for in our sandy soils in the first webinar, and then in our clay soils afterwards. So really today is an introduction to these concepts around physical, chemical and biological fertility. And then I'll be talking to you later about how to diagnose them and what to do and how to treat them if we have got some imbalance in these systems in your soils. So starting with physical properties, really the key physical properties of soils that are important are its texture, so the components of sand and silt and clay, also its mineralogy, its origin, its DNA, if you like, where did it come from, and what's its inherent fertility in the background, its structure, its strength, and its porosity, which is related to how well the soil can breathe and also take on and supply water to crops. Now, I've started with physical properties here. I don't like to give any particular preference to physical or chemical or biological properties, but I do think that physical properties are one that you should really look at because they're often overlooked. Sort of chemical properties are the ones that we tend to deal with the most in terms of nutrient management. But really, if you think about soil being the house that your crops grow in and your microbes survive in, and if you don't have a good house for these things, they will be unprotected, they will not be resilient, and they won't be able to provide the structure that your plants need to grow or the protection that your organisms need to keep your system firing. So let's dive into texture and mineralogy. So soil texture, the term texture refers to the relative proportions of various sized fractions within your soil. So if we think about what makes the soil, it's usually 45% minerals, 5% organic matter, and 25% air and 25% water. So you can imagine that if we have a soil which is really compacted, it might have more minerals in it and less air and less water. And that's not a place we want to get to. So we really want to try and keep that balance of air, water, and free pore space in our soils. And that's really determined by both the texture and the mineralogy of our soils. So the texture refers to the variable particle size fractions. So sand, which is anything greater than 20 micron, silt size fraction, which is between 2 and 20 micron, and the clay fraction, which is anything smaller than 2 microns. So really tiny particles. And it's not just the particles themselves in terms of their size that's important, but also their mineralogy. What's their origin? So a sandy soil through here in the southeast will predominantly be quartz. It's blown in from the beach. It won't contain a whole lot of other elements other than silica and oxygen. Where our clay particles, for example, and you can see I've got some photographs here, the top photograph of some sand grains, which measure there, you can see the scale bar I've got is 100 microns, so quite large particles in this case. Versus our clay particles, this is actually a kaolin clay, and knowing the mineralogy of your clay, so the type of clay that you've got present in your soil, is useful because it actually determines our inherent fertility. So the type of clay and the amount of clay that you've got will determine how much biomass you'll likely grow, the amount of nutrients that you can retain and supply in soil, but also the water holding characteristics and how well that soil will repair. And even though these clay platelets or crystals are really tiny in comparison to sand, and we can't see them by eye, what you'll notice in the southeast if you're out on the plains is that you can actually tell a kaolin clay from an illite, or a kaolin and illite more so, than a smectite. And I know I'm talking in big terms here, but smectite clays basically are the ones that shrink and swell. So if you've got some black country, and particularly if you're on the western side of the plains, either on the Narracourt or the Avenue or the Connemara, down to Millicent, you'll commonly find deeper, blacker clays, which will shrink and swell in the summertime if you've got country that that grasshoppers like to live in and explore in. It's often the areas where sheep will try and dig and camp in the summertime because those soils are really well aggregated. You can have a fairly good bet that those soils are dominated by smectite. Now, the other way you can tell is because the cation exchange capacity, which I'll talk about in a minute, will actually be bigger as well. So the soils themselves are more fertile. But on the other end, the grey clays, they're the ones that typically tend to disperse when they're wet and get really boggy and then set really hard. So there are some things you can do to try and determine the kind of minerals that you've got without sending a sample off to the lab. Now, ordinarily, it's very difficult to alter the soil texture unless you've got a sandy soil and you can clay spread it or you can delve it, which of course is something that we do throughout the Limestone Coast, both in the upper and the lower Limestone Coast. So we have been able to alter the texture of our sandy soils through here by clay spreading. But ordinarily, if you've got a clay soil, it's very difficult to do anything with that. And like I said, the mineralogy really determines how the soil physically behaves. So that sort of shrink swell characteristic, or does it just disperse and set really hard? But also about the supply of nutrients. So down on the plains, obviously, if you're closer to Mount Gambier, you might have some volcanic soil, and the minerals, the feldspar minerals in those soils as they weather can actually release phosphorus, for example. These clay platelets, like the kaolin and particularly the smectite, they can release potassium to your crop. So the proportions of sand and silt and clay and their underlying mineralogy are actually two of the first indicators of soil physical fertility that you can start to explore to see whether your soil is fit for purpose and is actually performing as it should. What I should just say here is that as you see the scale between the clay and the sand, and the clay being very small, you can see on this scale here of 10 microns, essentially you can see the wee little picture that I just put in here. This whole picture of all these clay particles essentially fits into about that space in the sand grain. So when we come to talk about, you know, water retention properties and cation exchange capacity and the protection of organic matter in soils, you can see that the surface area of clay versus the surface area of sand is many hundreds of times larger because the particles are so small and they arrange themselves in such neat packages. Okay, so the next two indicators of soil structure and of soil physical properties that are useful to explore are soil structure and soil strength. So healthy soils hopefully contain aggregates, and these aggregates can withstand external and internal forces and pressures. So what do I mean by that? Well, if you have a look at the photographs on the right-hand side here, I've got 3 different aggregates of soil that were all about the same size before I placed them in a dish of water. And we can see the first thing you can notice here in the soils, the 3 different aggregates, is the colour. You'll notice that this first aggregate here has a very dark chocolatey colour, indicating that it's a soil that supports really good plant production and biomass and has had good return of organic carbon back into the system. The aggregate in the centre is actually from slightly lower down in that same profile. So similar inherent sort of mineralogy, if you like, but it hasn't had those organic, those inputs of organic matter. And so the first thing that you notice is the difference in those 2 aggregates is the way that the aggregate in the centre has actually started to break apart. It's called slaking. As we go through time. So this is at 1 minute, a photograph at 1 minute after I've put the aggregates in water versus 5 minutes versus 10 minutes. So what you can see is that this aggregate here, which has got lots of organic material in it, it's also clearly supported lots of biological activity. The benefit of biological activity is that things like fungi can produce fungal hyphae, which will help to stick soil particles together. You can also get glues and exudates from other microbial elements in the soil, which will help also to glue them together, and then exudates from roots themselves. So you'll find that soils which are biologically active and rich in carbon will generally have a much better aggregation. So you'll see that they'll be nice and friable. You can sort of dig your hands through them quite easily. And then when you put them in a dish of water like this, they can actually withstand the stress of water rushing into the pores. And in fact, if you look really closely, you can see a little air bubble just escaping here from this particular aggregate. And you can see that it's a little bit bigger, so there's a little bit more water going into the pore after 5 minutes and a bit more air trying to push out. But after 10 minutes, the water has gone right into that aggregate, the air has come out, but the actual particle itself has been able to withstand the force of the water rushing into the pores. Now, the aggregate in the centre, the one from lower in the profile, actually hasn't been able to withstand that pressure, the force of the water going into the air pores. And so the water has rushed in and that particle has exploded. So after 10 minutes, we can see some fairly substantial disintegration of that soil aggregate, just with the influence of water. The aggregate that you can see on the far right-hand side, this yellow particle, this is actually from a different soil. This is from a sandover clay. And so this is the clay that's in the subsoil of many of our soils that are common through this district. And what we see here is this halo of fine clay particles starting to leak out from around this aggregate. And this is actually a chemical impediment. In this case, it's called sodicity that causes this dispersion to occur. It's from an excess of exchangeable sodium in comparison to the other cations in the soil. And again, I'll run through these when we do our webinar on clay soils and some of the issues that we experience in clay soils in the southeast. But just as an introduction today, these are some of the components of structure. And this is a really great test that you can do yourself with soil that you've collected. If you've got an area of a paddock or your farm which is not performing very well, go and dig a hole with a shovel and see how it feels under your feet. What's the structure of the soil look like? Is it really well aggregated around the roots? Does it take a lot of strength to actually get your shovel into the soil? Because strength is the other measure of soil resistance. And essentially, we're trying to see how much force can you apply to a soil before it falls apart, or how much strength or resistance is there in the soil, which could actually be stopping roots from exploring through the soil as well. So, sorry, Skyly, can you actually see the photo of me? I'm doing all sorts of hand movements, so I'm just wondering if you can even see is my camera turned on?
Yes, no, it's
okay, good. You can see me doing my dances. Okay, great, because I can't see that on my other screen here. So sorry.
I've actually just had a question come through.
Sure.
About this, so it's a good spot.
Yeah, sure. Why not? Yeah.
So in these cases, gypsum would only help sodicity, not dispersion. Is that correct?
So dispersion is caused by sodicity. So sodicity, the high exchangeable sodium or elevated exchangeable sodium, so more than 6%, is what causes this dispersion, this halo of small clay particles to occur. And the treatment in that case is gypsum, because gypsum being calcium sulfate, what you're doing is you're using calcium to displace the sodium, which is causing that dispersion to occur. And again, I'll go into that in our last webinar in a bit more detail around the chemistry of exchangeable cations and the balance of those. But yes, gypsum in this case would be the treatment for these dispersive sodic soils. So soil strength often increases as a soil profile dries. So if you are going to go out and have a feel around, if you've heard or seen the neighbours had a response to deep ripping, that's essentially overcoming a strength issue or a high bulk density, which I'll talk about in a sec, issue. If you're going to go out and have a feel around for those kinds of constraints yourself to see whether your soil, how physically fertile your soil is, it's really important that you do this when the soil is wet, not as it's drying, because they will become quite hard as they dry, particularly if you're in a sandy soil where you've got oxides of iron and manganese present, because these can actually cause your soil to cement as it dries. So these are the ones that will set really, really hard when they dry. Yeah, so just a couple of things to look out for there. You can measure soil strength, like I said, just by standing on your shovel and seeing how hard it is to get it into the ground in different spots in your paddock. If you test sort of near gateways versus underneath fence lines versus, you might have controlled traffic, so in your tram lines versus, in the interrow. You can use a penetrometer. I use a digital penetrometer. But the other thing is just a 10 to 12 millimeter rod with a point sharpened on the end, and you can push it in and you can feel for, where tight spots in soil occur, and then you can start to explore what the roots are doing in relation to that as well. So why do these things matter? So as I mentioned before, that the really, let me gather my thoughts here. Your soil type refers to the different proportions of sand and silt and clay in your soil. The structure really talks about its arrangement within the soil. And there's an example here, just with a couple of pictures that I've grabbed offline on the internet, sorry, online. All of these pictures that I'm using throughout my presentation, I have referenced in the bottom there. So if you want a copy of those afterwards, I can send all of the links through. But essentially, what you see here is a soil which has got aggregates. These little brown individual soil particles here are formed aggregates. Around that, we have a film of water in blue, and then in between, we have airspace. Now, this soil then has a lower bulk density. It would have a lower mass per volume and more pore space. This is what we're really looking for in a healthy soil or a healthy functioning soil, is soils that have got particles which are held together in some forms in various sized aggregates, lots of pore space, films of water around particles, and then also some air within those pore spaces as well, because of course, we need gas exchange between the roots and microbes in terms of oxygen and carbon dioxide and methane and nitrous oxide to be able to occur. And it can't do that if the soil is too compacted, which you can see with this image here on the right. Now we have lots of soil particles all jammed in together. And in this case, the soil is mostly saturated. You know, it's mostly water in between these small pores and only the odd air space. So this is a soil which is not going to function very well because your plants and your microbes can't breathe. The other important thing about, I guess, the content or the proportions of sand and silt and clay is its ability to be able to hold water. And you can see here in this image on the bottom that a sandy soil, for example, the maximum amount of water that a sandy soil will hold is only about 10%. Where if we go up to a clay soil, it can hold up to 40%. So if you remember before we had a look at those scanning electron micrographs, perhaps I'll go back to them. If you imagine that we have a soil which is all sand, so if we had a bucket full of this sand and a bucket full of this clay, and we thought about the pore space, and we put a hole in the bottom of the bucket and we filled it up with water, a bucket which is full of sand with very big pore spaces is going to drain very quickly. And not a whole lot of water is going to be left at the end. So, 10%, as I just said before, the maximum amount, and then it will drain down. Where a clay soil, because we have all of these particles so packed so close together, and we have very small pore spaces by comparison. If we did the same thing, we filled up a bucket with this kind of clay, and then we poured, 10 litres of water on top, what we're going to find is the infiltration rate will be very slow. But it can actually, because there's pores that are smaller, it can hold on to more water. But that influences then not only the amount of water that it holds in total, but the amount of water it can actually then give up to a crop which is trying to extract it. So we end up with then, I guess, this maximum amount or upper limit of storage water, or the total water that a soil can hold. But then the unavailable water is this water down here, which plants then can't extract because the pores are too small. But still, we end up with a bigger bucket of available water, if you like, to plants as we have an increasing clay concentration in our soils. So some of these properties, physical properties, are really important to understand. Things like soil texture, you can go and do yourself, and I might run through this in one of our future webinars about how to hand texture a soil and assess a bolus for its particle size, sand, silt and clay, and then also what's its likely water holding characteristics for those soils as well. But obviously, having a soil which is not too dense and not too strong, but strong enough to withstand external stresses is really important. Which brings me to key chemical properties of soils that are key indicators, I guess, of soil chemical fertility, and whether your soil is functioning at its best or whether it potentially is starting to be constrained. So the first of these I'm going to introduce is the cation exchange capacity. Then we're going to talk about pH, salinity, and then of course nutrients. So the cation exchange capacity, you might be wondering what I'm talking about. You may have heard it referred to as the CEC or the ECEC, which is a measure, it's actually an equation in the lab based on the exchangeable cations which have been extracted from a soil sample. But essentially, when I'm talking about cation exchange capacity, the way I usually refer to it is by asking the question, well, how big is your battery? Because clay particles, like the ones that you can see here, generally contain a net negative charge. What this means is that our clay particles are negatively charged, which means they can hold on to positively charged ions in the soil. Now, the most common positively charged ions in the soil are calcium, magnesium, potassium, and sodium. But if we're in an acidic soil, then we'll have elevated hydrogen and also aluminium, which can be toxic to plant growth and root exploration. So we're talking about how big is your battery. Essentially, a sandy soil is going to have a cation exchange capacity probably of around 4 centimoles of charge per kilogram of soil. That's the measure for the standard measure in Australia for cation exchange. Where the illite or kaolite soils I talked about before, the grey soils of the plains, they're going to have a cation exchange somewhere between 8 and maybe 12. So their battery, so we've just gone from maybe like a button battery to a AAA battery from our sandy soils to our grey clays, if you like. Then if we go to our black shrink swell smectite clays, they're going to have a CEC probably somewhere between 20 and 40, depending on how much organic carbon is also in that soil. And then if we jump to, so that's going to be maybe, we've just jumped up to a C cell battery. And then the other extreme, which we do have in the southeast, which are really not common in South Australia, are our peat, which I think it's questionable whether you call a peat an actual soil. I think it's just a mass of organic, decayed organic matter, but still, those soils have a large cation and anion exchange capacity. And so if you ever see a soil test come back with a CEC above 100, you can be confident that that's actually a peat rather than a clay soil, and it's your truck battery. So if we work through in terms of, the charge that our soils contain, just the same as a battery, really, they will increase generally as the clay content increases. There will be some changes with the mineralogy, but also organic matter can have an influence too. So it is possible to improve the inherent fertility of a sandy soil by increasing the CEC, and that's not, and we can do that by applying clay if you've got it, but the other way is to build organic matter in your soils as well. So we know that the CEC influences the retention of essential nutrients, so it can hold on to things like ammonium in the soil and phosphorus. It can provide some potassium. But it can also buffer against soil acidification too. So generally it's very difficult to alter the pH in a soil that has a lot of clay and a high CEC. And like I said, sandy soils, they really rely heavily on the organic matter fraction for their retention of nutrients in the topsoil. CEC generally is an inherent property, so it's related back to those minerals that we've got and the way that they've formed or been blown in or weathered, and it's not something that we can generally alter from a clay perspective, but is with, like I said, with the organic matter. So the next chemical indicator I'd like to introduce is pH. pH is a measure of the activity of hydrogen and hydroxyl ions. We measure it in the soil, we measure it in a 1 to 5 solution of soil to water. And it's a logarithmic scale. So if we've got a pH of 7, if we drop that pH back to 6, then we've got 10 times more hydrogen than the pH at 7. If we go to 5, then it's 100 times, and so on. So it's not a linear scale. So it's really important that if you see your pH dropping from 6.8 to 6.3 to 5.3 to 4.8, it's a problem and you need to fix it quickly, because the concentration of hydrogen in your soil has really ballooned at that point. So pH influences the activity both of biology in the soil, but also the availability of nutrients. So what you'll see here in this image on the right is, I guess, the availability of nutrients and also biological activity as our pH becomes more alkaline, so above 7, or acidic as we go below 7. So ideally, you can see that most of our nutrients are available in this range, sort of 6.5 to 7.5. And as we go outside of that, they start to peter out or become available in toxic concentrations. Things like boron, for example, can do that. So if we were down on the plains, if you happen to be a farmer on any of the grey or black soil plains, you most likely have a pH above 8.2 or 7.8 to 8.2, depending on your farming practice. And depending on where you are, again, in the landscape, if you're over on the western side and you do have lots of salt around in your soils, salts being not just sodium chloride, but also sodium carbonate and bicarbonate, you'll see that the pH can increase, and that's really common, like I said, on those soils in the plains. And as we get above a pH of 9 in water, we'll see, bacterial communities really start to drop off. Bacteria and fungi, nitrogen become less available and less cycling of nitrogen in soils. Phosphorus tends to get locked up in our really calcareous soils. And then things like iron, less available, manganese, boron can come into toxic concentrations, as can moly. Where if we go to sandy soils, so anything that's sort of deeper than 30 to 40 centimetres, I find typically is acidic below 5 centimetres in the 5 to 30 centimetre band through our sandy soils in the landscape in the Limestone Coast. What we find here again is that our biological activity will drop off, and availability of most nutrients pretty well stops. But we can see things like, iron and manganese come into solution, and aluminium, like I said before, which is really the toxic one, which can stop roots from really exploring down and accessing the water and the nutrients that are available deeper in the profile. So knowing your pH, not just in the surface, 0 to 10 centimetre layer, but below that is really important, because you might think that your soil is functioning well, but for some reason, you've noticed that your pastures are cutting out a bit earlier than they used to, or you've lost a bit of lucerne from the top of the sand dunes and you're really seeing sorrel come in, or you've got these patches of beans that have just, failed to thrive all year, where the wheat and the barley have been okay. And that's because different crops have different susceptibility to acidic and alkaline conditions. And of course, as they go through the season, they're trying to push their roots deeper into the soil, and that's commonly where we find these issues, not so much in the surface, 5 to 10 centimetres, but below that. So it's really important that we go looking well below the surface to explore what our pH is doing, so we can understand its interactions and relationships with nutrients and plants. Salinity is another, chemical indicator that I just wanted to raise with you today, because it is one that's quite common down the plains. Not so much up in our sandy country, up in the hills, because obviously we're up and out of the water table. But salinity is caused by a high concentration of dissolved salts, and that in this environment is commonly sodium chloride. And this has a negative impact on plant growth. And so you can see here in these series of 3 photos, the photo on the left, where we have a low EC, we've got increasing EC as we go across to the right. This is a photograph taken in, I think it was February, where we can see obviously the winter grasses have died off, that's fine, but we've got some chicory and some lucerne which have been actively growing over the summer period. This is a grey clay dominated by illite and kaolinite on the plains at Killara. And we can see as the salt concentration increases, we actually lose the lucerne. The chicory is still doing its best to hold on, but we don't have as many plants per square metre. It's starting to thin out. And then as our EC climbs, we really end up with these soils that are very bare. You can actually see some salt scalding on the surface here, some little white crusts. You actually see really good aggregation, and that's because when you increase the electrical conductivity of a soil water solution, it actually pushes soil particles together and actually makes them come back and form aggregates. So a really well aggregated soil sometimes can mean that it's saline in this environment. And you'll know that too from looking at the drainage systems through the limestone coast. If the water is flowing very clear, then it's most likely to be quite salty, versus a dam which might be very cloudy because it's full of fresh water and all of those clay particles have dispersed. So there is a relationship between salinity and acidicity, which again I'll talk about in the future webinars. Salinity has a negative impact on plant growth, and it's through osmotic processes. So as the electrolyte concentration increases in the soil water solution, the plants can't extract water anymore out of the soil, and so they will start to fall over because the salts there are too toxic for them. Salinity does occur naturally across the plains, and obviously it's influenced mostly by the groundwater. So what you'll notice, after the last few years, the water table hasn't come above the surface in 2019 or 2020. So we've probably had a leaching of salts through our profile in the last few years. If we happen to get a wet winter, and I hope that we do, and see our water tables come back up again, they naturally will bring a body of salt with them to the surface of the soil, certainly within the root zone, and those salts can then move through and accumulate in soils through evaporative processes. So, and as I said, the elevated sodium can influence the soil structure by pushing those particles together again. So it is one to look out for. Usually salinity is measured also in a 1:5 ratio of soil to water. And we measure the EC usually in decisiemens per metre. And I'll show you in a sec an example of a soil test result which provides those results. Okay, so the last chemical indicator I wanted to discuss today is soil nutrients. And look, I'll give you the hot tip. Soils don't need nutrients. Plants do. Actually, microbes do as well. So the soil cares not whether it contains nitrogen, phosphorus and potassium. It is the plants that really have a demand for these nutrients. And so I've just given a bit of an example there of, the NPK, so the nitrogen, phosphorus, K for potassium, S for sulfur, Ca for calcium, Mg for magnesium, and Cu for copper. The demands or the roles of those nutrients in plant function in this case. So things like chlorophyll, which relies on nitrogen and sulfur, photosynthesis needs nitrogen and phosphorus and potassium, amino acids and proteins are driven by nitrogen and potassium. There's a whole heap of processes that phosphorus is needed for in plants. And I can tell you that phosphorus is one of the nutrients, unfortunately, in our sandy soil environment, which is naturally lacking through the limestone coast. So if you are growing plants that have a high P demand, it's most likely that that demand will not be met by the supply or the weathering of the minerals in our soils, because like I said, our sands are mostly quartz. So if they weather, it's only to silicon and to oxygen, it's not going to supply phosphorus in the process. And if you have a look at our natural vegetation and native vegetation across those environments, they are, things like banksias and gums that have very low phosphorus demand and requirement. So when it comes to knowing how much nutrient we need in our soil, again, it comes back to the purpose that you're using them for. So how do we know if our soil has enough nutrients to meet your purpose? Well, the first way that you would do that, obviously, is by conducting a soil test. And usually for nutrient analysis, we look in the top 0 to 10 centimetres of soil. But if you do suspect that you've got an acidity issue or an alkalinity issue or some elevated boron or salinity in the subsurface layers, we would also recommend that you take a 10 to 30 centimetre soil sample and send that to the lab. Now, what kind of lab? You want a lab that's accredited with ASPAC, which is the Australasian Soil and Plant Analysis something accreditation scheme. Look it up. If you're going to send a sample off, make sure that the lab that you have sent it to is accredited in some form. But also understand the test sets that you're requesting as well, because they do vary. In South Australia, we commonly use the Colwell phosphorus test for looking at phosphorus availability in soils. Where other states will use different tests. And so when it comes to looking at the level that you've got and whether it's adequate for your crop need or not, it's really important that you know what test was used, but also the crop as well, because what you'll see here, if we have a look at the desired level for all of these different indicators here in the soil, is that they generally will give a range. So in this case, it's Colwell P, and I've asked for a recommendation, the desired level, to tell me how much phosphorus I need to grow a pasture. And in this case, we've got less than 5 milligrams per kilogram of phosphorus in the soil. And we know that we're going to need, 20 to 30 to grow a somewhat productive pasture or improved pasture in this environment. Now, these particular results that you can see here that I've presented, this is actually a soil sample, 0 to 10 centimetres, that I've collected from some native vegetation on a sand, obviously. And so you can see that in its native environment, soil in this particular instance is pretty well devoid of phosphorus. And we actually know that down on the black soil plains in the high rainfall environment, where we're pulling off, up to 10 tonnes reliably of wheat grain per year, per hectare, that these critical values or desired levels are actually more like double that, up to 50 milligrams per kilogram to meet the needs of the crop. So there are a couple of things that you need to know when you are doing soil tests. The first of those is, have you ticked the right crop type to get these values back? Because the values they report here will differ depending on whether you've ticked potatoes or wheat or canola or lucerne. And also know the test sets that you've requested as well. So if we have a look at this particular soil test, this is one of the standard presentations that you get from APAL, which is the lab in Adelaide. The first things we notice here are some physical indicators. So up the top there, it says MYR as soil texture. And so it's determined that the soil texture is a sandy loam. And it's determined that using a mid-infrared spectroscopy, which measures the proportions of the sand and silt and clay, which you can see down the bottom here. It says physical. So we're talking about physical fertility here. And we've got a clay percent of only 8.5%, 89% sand, 2.9% silt, which gives us a texture of sandy loam. So that's the first thing that to look for on your soil test results. Now, the next thing then are some of these chemical indicators. So here's the ECEC, which is the effective cation exchange capacity. And again, this is the sum of all of the cations that have been extracted from the soil. So the calcium, magnesium, potassium, and sodium, and possibly in this case, hydrogen and aluminium as well, because the pH is very low. And we're only at 3.56. So remember I said a sandy soil, the size of the battery in a sandy soil is only going to be about 4. Centimoles of charge per kilogram, and so here we are at 3.5, so that's about what I would expect. Organic carbon here is actually pretty good. It's 1.82, you know, for a soil which is otherwise just supporting native veg, but of course you'd expect that because there's no removal either from these types of systems because it's native veg. So all of the litter which is falling from the trees and the grasses is going back to the soil surface and is being retained and cycled there biologically, but we don't have any product removal. We don't have any soil disturbance. In this case, it was a scrub block which had been locked up, so no grazing through there, and certainly no cultivation. So still 1.8% organic carbon, which would certainly be higher than what we would expect in a sandy soil landscape, say in the Mallee, which has been farmed for the last 50 years. The pH in this case was 5.4 in water, and there's actually another test another extractant that we measure pH in, and that's calcium chloride rather than just water, and we see the pH at 4.3. So this is telling me that this soil is very acidic. And again, I'll go through some of these tests when we talk about sandy soils in July. And the other ones, here's our salinity, EC, electrical conductivity, and a 1 to 5 soil water extract. So this soil test is telling me, this result template is telling me the test, how it was measured. Here's its units, decisiemens per metre, so that's what I expect. And also the range that says, look, if you get above 0.15 in this case, that soil is going to probably be too saline and its sensitive species is going to start dropping out or losing productivity. But in this case, we're well within this range, and so we have an acceptable EC in this case. EC is something I'll also discuss. That's a conversion based on soil texture, and I'll talk about that in future webinars. So nutrients is the one we came to talk about in this case. So what we see here is that this particular soil, again, it's native vegetation, so it contains very low nitrogen, both nitrate and ammonium N. It has no natural phosphorus. The PBI, which is actually an indication of if we did apply phosphorus, how much of it would likely get tied up. It's in the acceptable range in this case. So if we did apply P, it would likely be available. We've got an indication there for sulfur. And then we've got these other trace element measures as well, which is standard in boron, iron, manganese, copper, and zinc. And of course, we know that a lot of these trace elements are important not just for plant health, but also for animal health as well. So it's important that you do have an understanding of not just the macros, but also the trace or microelements in soil too. So how do you know if you've got enough? Well, the other way that you can assess that is by looking at the nutrient removal of your product per tonne. So the yield matters here. If we just look at the concentration, for example, of wheat and canola, we can see that for every tonne of wheat that we remove per hectare, it's going to be removing nearly 18 kilograms of nitrogen, 2.4 kilograms of phosphorus, and so on. If we look at that in comparison to canola, canola has a much higher N removal, also phosphorus removal and potassium removal in terms of its kilograms per tonne, but we might only be growing 3 to 6 tonnes of canola where we're growing 8 to 12 tonnes of wheat in this high rainfall environment. So when you do the maths, and they're going to come out roughly equal. So yield matters in this case, and it's really important that you do know the crops that you're growing or the product that you're removing from your environment, and then also, its yield per hectare, so that you can make sure that your soil has got the nutrient reserves or the nutrients there in reserve to meet the demands, and hopefully replace what you're removing in some form. If we look at something like potatoes, for example, versus cattle, we see that for every 500 kilo steer that walks out the gate, we're going to be removing sort of 16 kilograms of N and 4 kilos of P, versus potatoes, which looks really low, but I can tell you that we're removing 60 tonnes of potatoes per hectare, where I doubt that we're removing 60 tonnes per hectare of cattle. So it is really important that you know, if you have had that centre pivot, which you usually use for, say, lucerne production, and you graze it and you've got a lot of manure going back in and it only gets irrigated a couple of times a year, and then you think, gee, the money's good, I'm going to contract it out and grow some spuds. Let someone else grow some spuds under my pivot. Be really mindful that the nutrient demands of a crop like that and its removal is going to be much higher than your system ordinarily has to supply. So when it comes to biological properties or functions in soils, really the things we're thinking about here are microbial communities and activity within the soil, the microbial biomass. Obviously, we want bugs both above and below ground, great predators. Hopefully we don't have too many pests. Biological functions really drive the decomposition of organic matter and also the cycling of carbon back through soils. And so the biological processes in soils are really important and underpin really their fertility, both of the soil and the plants that are growing in them. And again, often overlooked because you usually can't see what's going on. So the role of soil organisms, like I said, really, they really drive the decomposition of organic matter. So if you've got a stubble after harvest and you've left it standing up in the air and it's not in contact with the soil, there's not much that's actually going to break that down unless you put through, sheep or cattle. But really, the great value of those types of organic materials comes from their decomposition and recycling back through the soil, and it's the bugs in soil that do that for us. Like I mentioned before, bacteria and fungi can have a really important role in forming soil structure and soil aggregates through their glues and poos, if you like, but also through their fungal hyphae, which can help to hold aggregates together. They can actually regulate plant growth promotion as well through a whole range of different hormones and chemicals that they can extract to actually interact with plant roots in the rhizosphere, which is the very small area adjacent to plant roots as they explore through soils. It's a very rich microbial area. There's a lot of microbial activity that happens in the zone right around root tips as they explore soil. And there are relationships that can signal, different plant growth, either promotion or resistance or resilience to different climatic events as well. Soil organisms, particularly bacteria and fungi, also play a huge role in cycling and delivering and retaining nutrients and delivering them back to plants. Now, that's not just the nutrients that are derived through things like, recycling organic matter, but also critical processes for converting things like ammonium to nitrate. So if we apply, ammonium-based fertilizers to soil, it'll be the nitrosomonas bacteria which will actually convert that into nitrate and be available to plants, but also then potentially for leaching as well. So they do control a lot of these processes and conversions of nutrients and mineralization of nutrients in soils. They can help to break down pesticides and herbicides, and they can also provide protection from soil-borne pests and pathogens. Plus, they do regulate our water quality, and of course the soil does this, but a healthy soil will do this, and also the fixing and release of greenhouse gases such as nitrous oxide, carbon dioxide and methane. So a huge amount of roles that are played in soil by such tiny things that we can't see most of the time. And of those tiny things we can't see, if we have a look at these different organisms that we find in soil, the microflora, which are the bacteria and the fungi I was talking about before, and the archaea and also viruses, these are things that are smaller than 5 microns. And their functions, their primary functions really are to turn over organic matter. It's this nutrient mineralization, so they can, consume this organic matter which is in the soil, which has come from both, organic residues on the surface, but also roots, manures and urine as well. And they can immobilize these things as they're decomposing, but then also mineralize them and become available again in plant available forms. And they're really vital for aggregate formation, like I said. So they play a huge role both chemically and physically in the soil too. If we go to our fauna within soils, so these are living animals within soils, we have our protozoa and our nematodes, and they actually regulate the bacterial and the fungal populations. And so these guys feed on these guys, and again, are really useful in nutrient cycling and availability in soils. If we come up in size to our mesofauna, we've got some things like collembola and mites, which again do all of these things above, so regulating bacterial and fungal populations. But they can also fragment plant residues. So these guys are a bit bigger, so they can chew down on bigger plant residues. They actually help to stimulate the microbial activity, and they can create biopores. So if you've got mites and things crawling through soils, obviously they can help to push soil particles apart and actually create some small pores for the other guys to live in, but also for air and water in soils. And then if we come to our macrofauna, this is our termites, our ants, beetles, earthworms, and spiders. These guys are really our ecosystem engineers. These are the guys that really, they do all of the things that the mesofauna do, but they can also redistribute organic matter and microbes back down through the soil profile. So because these guys are quite big and they're quite strong, they can burrow their way through soils, and they can really transfer other microbes and organic materials down deeper into the profile. And this can have an impact on the drainage, it can have an impact on the root exploration, and again, they're really vital for aggregate formation. So, all of the life, if you're a farmer, please don't just think about the livestock that you farm above the ground, but also the livestock that you farm below the ground, because really it's these guys that are helping to determine, the fertility and the function of those other systems in your soils. So one thing I didn't talk about in the chemical section before was organic carbon, which is often referred to as a chemical property. And the reason I didn't is because organic carbon in soils, its cycling through soils is really closely linked to the microbial biomass and the activity of microbes in soils, and those other organisms that live in soils as well. So I like to put the two together because you won't have one without the other. Where you do have more carbon, you will have more microbial biomass. But the total amount of microbial biomass that a soil can hold, if you like, is really determined by clay. And again, Amanda Chappell is going to talk to us about this in our next webinar, because this is absolutely her field. And then the negative impact on that is the depth of that, or the depth of the soil. So soil type has a big impact on how much microbial biomass your soil can support. Rainfall also impacts on that. So if you're in a low rainfall environment, your soil is not going to be as microbial active. And then the actual microbial biomass that you then actually can support in soil is really the result of your management. So we know that there are things that can positively influence, management activities that can positively influence the microbial biomass that you have. And that's things like incorporating legumes into your system, or having pasture delay phases, no-till, or correcting a pH issue, or composting, or growing a a polyculture, a multi-species cool season or warm season cover crop, for example, can all help to boost. They're all management practices that can help boost microbial biomass in soils. And if you have a look at this graph on the other side here, again, I've pulled these from the soil quality website. You'll see here that there's a really strong relationship between the microbial biomass carbon and the total soil organic carbon. So you'll see that here's a potential, attainable as organic carbon increases, and this is a whole heap of soil samples from Western Australia. So these two measures are really closely related. So I'm not going to go into carbon in any more detail than that, because again, Amanda's going to cover that for us next time. So I guess in review, what makes the soil fertile? Well, really, a fertile soil is one that is functioning really well, and that's a soil that's got good soil structure. it has good stability and good porosity. So it's not too compacted, it's not waterlogged, there's good movement of air and water through the soil, and it can withstand things like, you know, the force of water running into pore space. It doesn't blow apart. So you can do that little aggregate stability test like I showed you a few slides back. The soils have the ability to retain and supply nutrients, and this is both a function of its texture, so how much clay is there, the mineralogy of that clay. You know, is it a lower you know, fertility clay like a kaolinite versus a smectite? How much organic matter have you got cycling back through the soil, and how much carbon does it support, because that's the food source for microbes. So you want a soil that can retain and supply nutrients. You really want the pH to be in that ideal range to ensure the best availability of nutrients. Availability of nutrients is also determined by things like microbial activity and also, you know, aeration within the profile as well. So, you know, you can have the ideal pH and still not have available nutrients, but this is one thing that we can actually correct and have an influence over. So make sure you do, you know, go and have a look for those issues. No toxic elements, so not too much boron and not too much aluminium and not too much hydrogen, and you know, not too much salt or, you know, excesses of exchangeable sodium, which are going to cause, you know, those structural issues in soils too. Obviously, we want nutrient reserves that are sufficient to meet your purpose. You know, if you're growing native flowers, you know, Banksias, then you're not removing a lot of phosphorus. But if you're growing 60 tonnes of potatoes, then you are. So you want nutrient reserves that are sufficient to meet the purpose, you know, of your business enterprise. And you don't have to supply them in a synthetic form. You can certainly look for, you know, organic sources or more natural sources of things like, you know, phosphorus, you know, calcium as lime. There are a whole heap of different biofertilizers available. Obviously, you want an active and diverse microbial community, and you want the presence of these ecosystem engineers. You know, if you go out to your paddocks and you find that your cow pats haven't been dug over by dung beetles, then there's something probably wrong. You know, I can tell you that the cow pats at the moment at home are just, I can't believe how quickly they are being turned over and incorporated back into soil. You know, dung beetles really have to be the best thing in a sandy soil. Worms, you know, have a look for them. You won't find a lot of worms in a really dry, sandy environment, and that's where things like ants and termites are really, you know, the guys that are transporting things around. And you'll see that in a dry, sandy soil environment, that ant mounds will be, you'll have colour at the top because the ants have actually brought some clay material from lower in the profile and brought it to the surface. So those guys are making the macropores for air and water that get through soils. So have a look for your ecosystem engineers. So my take-home messages for today, you know, the fertility of your soil, it really is determined by the combination of those inherent properties. So the ones, you know, like the DNA of your soil, so its minerals and the proportion of those minerals and the size of them. And then, so your inherent properties plus your dynamic properties. So these are the things that you can actually alter and have some influence on through your management. The interdependent functioning of the physical, the chemical, and the biological systems determines how productive and profitable and resilient your soils are going to be. And I'm guessing that most of us are in the game of trying to, you know, produce a product, a commodity from our soils and sell it to derive an income. And obviously, we want to keep doing that into the future without having a detrimental impact on the soil itself, or on our bottom line, or on the greater environment. And, you know, healthy soils, they really do provide vital ecosystem services, not just to nature, but also to humanity, through the purification of air and water and the, you know, the production of good, healthy, nutritious food for animals and for humans. So please, please nurture them. I absolutely encourage you to dig deeper when it comes to exploring your soils. Don't just rely on a 0 to 10 centimetre soil test that you've sent off for nutrient fertility, because while it can tell you a lot, you can learn a whole lot more by, or alongside that, by digging some holes and having a look for some of these other critters in soils and where roots are growing and how plants are thriving or not. Some acknowledgements and references. Obviously, the soils of South Australia are of Southern South Australia. I mentioned this one's last time. You know, James Hall, Dave Mashment, and Bruce Billing. This is an amazing book and a great resource for South Australian soils. So get your hands on that one. A lot of the interpretation of soil tests today that I've talked about have come from interpreting soil test results and what do all the numbers mean. This is a very good resource for understanding physical and chemical indicators in soils. The book Soil Health, Soil Biology, Soil-Borne Diseases and Sustainable Agriculture, again, written by Australians Graham Sterling, Helen Hayden, Tony Patterson and Marcel Sterling. Another fantastic resource that explores obviously soil biology. So, interpreting soil test results and the soil health and soil biology book really are my Bibles when it comes to, exploring and interpreting what's going on in our soils. And like I said, a couple of the images and graphs and data that I showed you today have come from a fantastic website called soilquality.org.au. If you go to that website and there's tabs there for Western Australia, South Australia, Tasmania, New South Wales, Queensland and Victoria. You can go to the state of choice and there's a whole range of fact sheets in there on biological, chemical, physical indicators in soils. There's also some really great snapshots as well, so you can see where you fit with things like soil carbon. So that's a really fantastic resource. You can download the fact sheets off of there to print as well. With that, I will see you again on the 28th of July. Next you'll see Amanda Chappell, and I will join for that one on the 23rd of June. And then you'll see me on the 28th of July and the 18th of August, where we will look at these indicators of soil fertility in sandy soils and clay soils, how to go about interpreting them or diagnosing them, interpreting and treating them. So thank you so much for joining me today.